This video demonstrates the development of an AI-enabled predictive maintenance use case in the aircraft domain. Traditionally, the strategy to address the equipment failures is to conduct preventive maintenance at regular time intervals, which incurs higher than necessary maintenance costs and can be difficult to adapt to a changing industrial scenario. When the equipment is instrumented with sensors, the future problems can be detected in real time to enable the on-demand maintenance, which in turn leads to savings concerning the maintenance costs. The well-known NASA's turbofan engine degradation dataset will be used to showcase how ALEX can solve the predictive maintenance task. The dataset consists of the time series data recorded from multiple sensors and the condition stages such as the air pressure. It is required to predict the remaining useful time of each turbine given the recorded data. The first step is to connect the data stream to the ALEX predictive maintenance analytics. The data stream is represented by the CSV files that get uploaded from the equipment monitoring system at regular intervals. All the available sensor types can be revealed by providing a sample file. There are 21 sensors and 3 external conditions in this data stream. Also, we will mark which of the CSV fields carry the engine ID, and which of the fields carry the timestamp, so that ALEX could apply the time-aware AI. After that, the new stream can be connected. We define which of the stream's fields will be stored per engine to enable the predictive analytics. We only need the telemetry timestamp and the value of the remaining cycles to start learning. ALEX will decide whether it is required to store the other data fields per engine automatically. The next step is to create an AI project in ALEX. We specify where to get the data from. It is the turbine's telemetry stream we've just defined. Also, a proper constraint will be applied to make sure the learning data is valid. There are no features available for machine learning at the project start. We can only use timestamp and the remaining lifetime value received. We enable the time-aware modeling mode because the turbine sensors provide time series data. The rolling window should be defined. The automated feature generation will be conducted. Now we proceed with the model creation. Some important parameters, such as the model's metric, the type of model, and where to get the target value from, are specified there. The baseline model uses just a few default features to start the learning process. ALEX Predictive Maintenance Analytics track the sensor streams and automatically builds features that provide the best model quality. The more data arrives, the more relevant features get generated and the better models will be built. The recommended features are incorporated in the new model version with just a few clicks. We choose the features that were suggested by ALEX and create a new version of the model. The existing models will keep being trained using the previous versions of the feature set, and the quality can be compared across all versions. ALEX conducts the algorithm selection and hyperparameters optimization without a data scientist. We can drill down to any specific model from the Models tab of a project. The Summary tab of the model page reflects the model's evolution. ALEX allows to track which features are used by a model and what the respective feature's importance is, facilitating the model's interpretation. The Model's Evaluation tab shows the model's metrics, including those calculated at the train, holdout, and test data. The metric's value can be matched against the model version as the learning process is continuous. The Hypothesis tab shows which algorithms are used with their hyperparameters. The History tab shows the model's lifecycle log. We will set the remaining lifetime threshold to 20 cycles for predicted future value so that Alex could apply the model to the data stream and act preemptively in case an engine approaches a wear-out zone. We use a Prediction Context tab for that. Multiple prediction contexts with different thresholds can be defined for different prediction scenarios. We arm a conditional rule that monitors the predicted remaining useful lifetime value per engine. Once the predicted value hits the threshold, an arbitrary action can be triggered, from simple notification to an automated maintenance schedule adjustment. Alex can orchestrate multiple third-party systems if required. Alex enables a REST endpoint to obtain the predictions. The REST API does not expect any feature value to be passed. It only requires the engine ID. Alex calculates the features by itself. It is often possible to represent a machine learning task in multiple ways. We started with a remaining lifetime prediction using a regression model. However, Alex allows arming a classification model using the same data. We will map the raw remaining lifetime values using the domain-specific rules, provided that the value below 20 cycles indicates the engine is going to wear out soon. The low RUL value is our class of interest. F1 metric is used to balance precision and recall. The same features we use for the regression model are also applicable here. The algorithm's hyperparameters will be found automatically. The Classification Model Summary tab displays the information about the class distribution, as well as the feature importance chart. Most of the relevant classification metrics are available at the Evaluation tab. ROC and PR curves help to estimate the model's performance. The confusion matrices allows us to trace how many samples were classified correctly and how many of them were misclassified in the hauled-out data set. The Alex models are explainable. We can request the explanation and navigate through its results at the Explanation tab. Alex shows why a specific model predicted such value for chosen samples of data, allowing to compare the model's outcome to the domain knowledge. Each explanation contains the top features impacting this prediction, what their values are, and how those values impacted the prediction outcome. We can set a proper decision threshold for a classification model at the Prediction Context tab, depending on the business goals. Alex will guide the decisions by providing the estimates for the number of the correct predictions and misses based on the probability threshold. We set the probability threshold to 0.87 to make sure the false positive rate is low. Alex platform facilitates fast deployment of the end-to-end predictive maintenance use cases and does not require any deep data science expertise. It takes minutes to hours to obtain valuable results. Thanks for watching, and find more information at dstreams.ai.